morning, everyone. So today it's a pleasure to have Feixiong's defense. So he has worked with me and Ray on content delivery for information-centric network.
Thanks for the introduction. So my topic is mobile content delivery in information-centric network. I will first talk about the motivation, then I will dive deep into the 4 major projects that I have worked on. So the current internet is mostly used as a platform to serve content and services. When we are connected to the internet, most of the time we are accessing this content. For such content-oriented use cases, we care about content, not network location. In addition, more and more mobile devices are connected to the internet, which implies the surge of mobile data. Such 2 trends motivate us to rethink about the mobile content delivery techniques. However, the current internet is built upon a location-based internet architecture. For example, in this figure, these 2 end hosts are connected to the internet, while the clients want to access the content. The internet always needs to first identify the 2 IP addresses and build an IP connection between these 2 IP. The data communication is then carried out beyond this IP connection. As we can see, this is a point-to-point communication model between these 2 IP addresses. In addition, the internet uses an end-to-end protocol stack, in particular TCP, which lacks the support for in-network storage and processing. Such model contradicts with information-centric usage pattern, as we can see in the other figure here, which shows an ideal information-centric pattern, in which the client could explicitly express its content request and then the network retrieve the content back. To support content services, the current internet uses an overlay-based solution. Examples including CDN and P2P. However, these solutions are mostly built upon TCP/IP and requires some complicated application layer protocol to resolve and redirect a request to a fixed IP location. Such model is heavily restricted by the underlying IP, which might be less efficient. Therefore, the research community proposed the information-centric network, which tries to facilitate content service from a network architecture perspective. The information-centric network is centered around a name-based service. So it defines a network object by its unique name. And so the client could directly utilize this object name for network communication without requiring to resolve to a fixed location at the first place. Such direct addressability of objects at the network layer enables the location-independent communication model, thus provides native support of mobility. Examples of ICN including MobilityFirst and the Content-Centric Network. Information-centric network also provides inherent support of content caching. So a content might be widely distributed under the same object name, and the request can be served from nearby cache using that name. As an example of ICN, MobilityFirst uses flat GUID as object name, and this GUID is separated from network address. It uses a global name resolution service to manage the mapping from GUID to network addresses. MobilityFirst also supports an extensive in-network caching, like in-network service like content caching. Another example of ICN is content-centric network. Content-centric network use hierarchical name to identify a content. So here, a large content might be segmented into multiple data chunks, and each with a different hierarchical name. So here is an example of such name structure. CCN also defines 2 packet types, interest packet and data packets. Both types specify the content name, and it uses a interest data communication pattern. So the client issues an interest to request the data with that name. The CCN router uses 3 data structures for packet forwarding, including the forwarding information base, pending interest table, and the content store. The forwarding information base is similar to the IP forwarding table, but it uses a name-based routing approach. The pending interest table tracks the outstanding interest, so when the data comes back, it knows which interface it should return. And the content store is the router cache store. So the work of my thesis is centered around the content delivery technique in ICN. So first, I have looked at what the content transmission characteristic would look like in ICN and propose a transport protocol for such kind of network. In addition, since caching is a very important component in ICN, I then look at the content caching and the prefetching schemes in ICN. Beyond this, I've looked at how we can utilize this technique into real use cases. So I have worked on a satellite-based video delivery system that could utilize the technique that we have developed into a real use case. In particular, I have proposed a transport protocol for CCN, look at edge caching and prefetching framework for MobilityFirst, and also conduct a cache scheme comparison in ICN. And last, I have worked on a satellite-based video delivery system using MobilityFirst. So next, I will talk about my transport control work. I will first analyze the content transmission characteristics and then describe our transport protocol. This work is done in a CCN context. So let's look at what the content delivery characteristic would look like. So when the client wants to request a content, it will need to issue a bunch of interest packets, one for each data chunk. And since the CCN uses a name-based routing approach, each interest might be forwarded to a different content source. So for the first interest, it might be forwarded to the content server, which returns with that corresponding data chunk. And for the second interest, the corresponding data might be already cached in the network. So an intermediate router returns with the data. For the third interest, another router might cache the data and return with that data chunk. As we can see, this is a receiver-driven transport, since the receiver issues interest to request that data. And also, the data might come from multiple data sources. Therefore, the sender-centric TCP might not fit here. In addition, this is a hop-by-hop transfer, since at each hop, it conducts advanced processing other than simple forwarding. So the traditional end-to-end protocol doesn't fit here. Also, this is a multi-source, multi-path transfer, since we might have multiple sources for different data chunks. Therefore, there's no explicit endpoint here, and we cannot use RTT to indicate congestion. Beyond this, we then propose our transport protocol called CHoPCoP that is well suited for CCN content delivery characteristic. In addition, we extend CHoPCoP to a parallelized version that could support multi-homing at the client. So now let's look at our CHoPCoP design. So this figure shows the overall design of CHoPCoP. We have receiver-driven hop-by-hop transport. So the receiver issues interest to request each data chunk, and it controls the interest issuing rate. We also use a chunk transfer at the sender and at the receiver side. We use explicit congestion notification to indicate congestion, and we use a fair share interest stripping to realize bandwidth sharing among flows. And we have AIMD-based receiver interest control at the receiver. So next, I will talk in more detail about each design components. The chunk transfer. The rationale behind this is since CCN data chunk is large in size because of extra header fields like signature and signed info. To avoid layer 2 fragmentation in the network, we have this chunk segmenter at the sender. So the sender segments the chunk into packets, and these packets are forwarded in the network. So at the receiver side, we have a chunk aggregator, which will aggregate this packet into chunk. And we also just mentioned that in CCN, we have this multi-source, multi-path transfer. So we can neither use RTT value nor the packet arrival sequence as indicator for network congestion. Therefore, we decide to use explicit congestion notification for congestion detection. Here, the intermediate router estimates the congestion level by its memory consumption and mark data packet according to a mark probability function. So at the receiver side, when it sees this ECN signal, it could reduce its interest shrinking rate. Beyond this, we propose a lightweight flow-aware network paradigm to realize fair bandwidth sharing among flows and also avoid overload because of malicious receivers. Since the malicious receivers might not cooperate with the ECN, so we have this fair bandwidth flow-aware network scheme to avoid that. For our flow-based interest control, it utilizes a diffeasive round robin for flow scheduling and is triggered to delay interest when ECN is insufficient. For that, we define a flow's queue requirement according to this equation. So here the QD refers to the current buffer occupancy of the flow's data, and the QI refers to the buffer needed in the near future because of the flow's outstanding interests. So the applet queue measures the total queue requirement of this flow. And we delay this flow's interest according to the delay probability function. From the function, we see that this Qmin here is larger than the Qmax from ECN. This is to ensure that the FISP is not triggered to delay interest unless ECN is insufficient. To cooperate with ECN, we implement an AIMD-based receiver interest control at the receiver side. The receiver then detects congestion when marked packets are received. And for interest window size W, if a complete chunk is received, the window size is increased additively. However, if an ECN marked chunk is received, the window size is decreased by a factor of beta. For beta, we propose an adaptive window size decreasing scheme according to this equation. So in the equation, nmark refers to the number of marked packets in the chunk, and n is the total number of packets in the chunk. And beta 1 and beta 2 are two parameters. So here, with larger number of marked packets, it means that we might have more severe congestion in the network. So the beta value will be smaller. This means that we will decrease the window size more. We also have this interest timer and the retransmission for reliability at the receiver. But this should seldom happen because we use the ECN scheme. We have mentioned that we extend CHoPCoP to the parallelized version for multi-homing use cases. One example is mobile phone. A mobile phone might have multiple network interfaces, and we might want that the mobile phone utilizes its multiple interface for content transmission. So we see that this pCHoPCoP receiver here, it contains a pCHoPCoP controller with multiple CHoPCoP engines. Each CHoPCoP engine manages a specific network interface. So this idea is analogical to MPTCP.
So before you go on that slide, so can you describe a little bit about what the assumption is about the layer CHoPCoP assumes underneath it?
So right. Underneath CHoPCoP is the network interface. So each network CHoPCoP engine manages one network interface. For example, for a mobile phone, if it has two interfaces, one with LTE, the other with Wi-Fi.
Right, but does it assume that it's on like a layer 3 that it can globally route packets somewhere, or does it assume it's more layer 2 that it has to do the routing?
We assume it's kind of layer 3, and when we push down the interest, it knows it was
okay, so you're assuming interest. Something like NBN where it has interest.
Yeah. Okay. So let's look at how pCHoPCoP controller and CHoPCoP engine works. So the pCHoPCoP controller controls the cooperation and the progression of CHoPCoP engines. It manages the interest scheduling among all the CHoPCoP engines, while the pCHoPCoP engine manages the data delivery over its network interface, in particular the congestion control. So the pCHoPCoP controller has two major data structures, the interest space and the CHoPCoP state table. So the interest space contains all the interests that the application requires, while the CHoPCoP state table manages all the state of each CHoPCoP engine. So when there is a space opening up in the CHoPCoP engine's interest window, it asks for interest from the pCHoPCoP controller. So the pCHoPCoP controller assigns an interest to that engine from its interest space. And when the CHoPCoP engine receives a complete chunk, it can push that chunk to the pCHoPCoP engine. So we have implemented a complete protocol at user level and conduct a detailed evaluation on the Orbi testbed. In the evaluation, we compare our scheme with several other CCN transport protocols. For these three protocols, they use a receiver interest window control, but they mostly use RTT for congestion detection. So we first look at this benchmark evaluation. In this scenario, A is the content server and C is the receiver. And we compare our scheme with other CCN transport protocols. So this figure shows the receiver window size, and this figure shows the instant data rate at the receiver. Well, this figure shows the number of timeouts happening at the receiver, and this figure shows the queue size at the router. From this figure, we can see that our CHoPCoP protocol, which is the red line, ends up with a much smoother interest window, a higher instant data rate with no timeout taking place, and a much more stable router queue. All of this results in a higher throughput for CHoPCoP. So next,
so can you go back, so one more slide. So can you just say a little bit about what the other two protocols were?
Yeah. So for all these protocols, they also they use a receiver-driven control. At the receiver, they control the interest sending rate, but they use RTT for congestion detection. And also, so ICP and HR ICP, they have a relatively small timeout setting. So that's why we can see that for here, we can see that ICP and HR ICP, it's frequently timing out because of its small setting of its timeout calculation.
So if they increase the timeout window, will that problem go away?
That's the ICTP. So the ICTP, it doesn't have that small timeout setting, but since it uses RTT, so it can only wait until the congestion happens, and then it decreases its window a lot. So we can see that its interest window is like a zigzag, but this actually impacts its performance. As we can see, when the interest window decreases a lot, the instant data rate will have a jump here, and then it has to go up a little bit. Instead, for our case, we use ECN. We have a much smoother window size. So this communication pipe is always saturated in our case. So and therefore we reach a more better throughput.
Feixiong, I don't know if other people asked this question. One of the reasons why you are doing CHoPCoP compared to ICP or any of the others is because you can deal with multiple sources of data, right?
Yes, yes.
How do you deal with the congestion issue then with ECN?
Yeah, so the idea here is since it might have multiple sources, so we cannot use RTT. But when the congestion happens, the router can actually detect whether this congestion happened or not. And if it the router detects that, then it will mark the packets. So at the receiver side, then it can receive, see the indicator for congestion, instead of just using the RTT to detect that. So yeah,
remember in your parallel CHoPCoP, you have a separation between the congestion control component and the flow and reliability piece.
Yes.
With your parallel CHoPCoP controller. So do you end up using a similar thing here for the congestion control piece for each source of data?
Yes. Yes. So yeah, in our pCHoPCoP, the CHoPCoP engine uses the same algorithm of the CHoPCoP we just mentioned, but we have upper layer, the pCHoPCoP controller that manage each interface.
Right.
Yeah.
You have results on that in your thesis, right?
Yeah. I also have results for the multi-source multi-pass scenario, but because of the time constraint, I only show this sample result for the CHoPCoP. Then I look at this performance of the pCHoPCoP. So I mentioned that pCHoPCoP is designed for the multi-homing scenario. So I use 3 topologies here. In the topology, A and B are content sources, which contain the same content. And E is the receiver. And we can see that E contains 2 network interfaces. So for this topology A, these 2 paths are symmetric, while the second topology, these 2 paths are asymmetric. While for the topology C, we have a wireless interface at the receiver. So we look at these 3 topologies and measure the throughput at each CHoPCoP engine and the pCHoPCoP controller. And this figure shows the throughput result. And from the figure, we can see that our pCHoPCoP protocol can aggregate the bandwidth of the receiver's multiple interfaces and achieve a much higher throughput. So we can conclude that our CHoPCoP protocol could well adapt it to CCN transport when we use ECN instead of RTT, and we have this the receiver interest control to adapt to the congestion. We also extended to the pCHoPCoP, which could effectively realize bandwidth aggregation over all the receiver's network interfaces. So we have looked at how the content transmission looks like in ICN. We then look at how we can do caching in ICN. For the caching and prefetching framework, it's conducted in the MobilityFirst context. The motivation of this work is that because of dense deployment of wireless access networks, we might transit across multiple access networks within a single content session. This becomes even more common in an urban vehicular environment. Therefore, we want to look at how we can facilitate mobile content delivery across multiple networks. For this, we propose EdgeBuffer, which we utilize edge storage as a distributed caching system. We partition a cache storage space for cache buffer and prefetch buffer. And we use a network level mobility prediction to guide prefetching. So this figure shows the overall EdgeBuffer scheme. We can see that we utilize the edge storage here, and we divide it into a separate cache buffer and prefetch buffer. For the cache buffer, we implement a popularity-based content caching, which could capture long-term aggregated content access pattern. While for the prefetch buffer, we implement a mobility prediction-based prefetching, so it could capture the short-term user access pattern. Therefore, we are trying to utilize mobility information here to enhance traditional caching. So next, I will focus on how we do this prefetching and prediction thing. So we use a network-level mobility prediction to do the to guide the prefetching. So why network-level mobility prediction? traditionally, people use individual user-based mobility prediction, but the assumption is predictable user mobility pattern. However, this might not work well for an urban area with complex road networks and frequent traffic congestion. So I have shown a figure here, which is from San Francisco taxi trace and shows the residence times of a taxi at the same AP. And we can see that the residence times vary quite a lot. Therefore, we use a network level mobility prediction in which the edge network makes the prediction for its connected clients. The rationale is that the edge network could aggregate mobility information from all its connected mobile devices. Such prediction, therefore, can adapt to traffic variation and might be more accurate. For our prediction, this predictor is located at each edge network. So each AP has its own predictors. And we dimension this prediction as two parts, the spatial prediction and the temporal prediction. The spatial prediction predicts what the next AP the client might move to. And for this purpose, we build a network transition probability table, which we use second-order Markov chain here. Since the Markov chain model is proven to be quite accurate for such spatial prediction. So for the predictor, when given the previous AP, it will return the next APs with its probability. For the temporal prediction, the predictor keeps a window of history residence times and extracts the statistics for residence time estimation. So when given the previous AP of the connected client, it returns the residence time of this client at the AP. So we built this predictor using GRS messages. Since GRS keeps track of each mobile client's network trace, when the GRS receives an update because of a client's movement, the GRS then sends back an acknowledgement to both its current network and the previous network. In the acknowledged message, it contains the client's current and the previous network addresses and the timestamp. So the edge network could connect these client traces from the GRS message and then build its own predictors. Since our predictor is directly built from the GRS message, there's no extra overhead. Let's look at the overall content prefetching protocol here. First, the client associates with a new AP, here AP1. Then AP1 conducts a temporal prediction and predicts the client's residence time. In addition to this, AP1 conducts a spatial prediction, so it predicts the next APs. Here, it predicts AP2 and AP3. So it sends out a prefetching message to the next predicted APs with the content ID and the initial chunk ID. And then the next AP computes the prefetching range and conducts the prefetching if that content is not cached yet. So we have implemented a discrete event simulator for the evaluation. In the simulation, we generate a mobile access workload by combining a San Francisco taxi trace with the WeGo AP database. For the WeGo AP database, we are trying to clean up the database a little bit and merge AP within certain distances. So we look at these two distance values. And we look at these two evaluation metrics, the prediction accuracy and the hit ratio. So let's first look at the spatial prediction accuracy. Here, the x-axis is the number of next APs that the predictor predicts, so that the client might move to one of them. And the y-axis is the accuracy of such prediction. From the result figure, we can see that our, so here we compare our network level prediction scheme with user-based prediction scheme. And we can see that our network level prediction scheme performs much better than user-level prediction scheme. In addition, when the k-value is 3, we can see that our network-level prediction achieves a very high accuracy, which is as high as 0.9. Next, we compare our EdgeBuffer scheme with several other caching strategies. The first is a pure LRU cache. Second, we use a pure popularity-based cache. For the third one, it uses a popularity-based cache with user-level prediction-based prefetching. And the fourth one is our strategy. So in the evaluation, we assume the client's request follow a ZIF distribution. And we vary the ZIF explosion parameter and look at the cache hit ratio for different schemes. With larger ZIF parameter, it means that the request distribution is more skewed, which means more requests falls into a small subset of popular content. And we can see that all these strategies converge to a very high hit ratio.
So, right, so for your workload that you're generating, you generate synthetic workload based on the ZIF distribution, or did you use some workload and modify it?
So for client request, we use ZIF distribution.
But it was synthetic, it wasn't like from a trace of something else, it was like a synthetic
It's
workload.
synthetic, yeah. We use a synthetic so we can look at different ZIF parameters and look at the performance.
All right.
So can you remind me of the mobility assumption here?
So for the mobility, actually we use this San Francisco taxi trace. It has
Trace-driven.
it has all the locations.
So those results are for the traces that you have.
Yeah, also this prediction accuracy also from that trace.
So this, I really like this piece of work. I think it's has some very nice element in it. The reason I'm still puzzled why it didn't get accepted at a better place, but but we sent it to Infocom, and the Infocom, what was the main complaint?
The main reason is there's not too much theoretical work when we send to
Okay.
Infocom.
Right.
So KK, do you have any comments?
No, I didn't hear the questions, but I'm fine with this. I'm familiar with this work. So
Yeah. KK was really familiar with this work. So I think there's a lot more to do here just to make it more impactful, right?
Yeah.
So right now its impact is very limited just because the question Rich just asked. Because the content access distribution is totally synthetic, so
Yeah.
there's very little truth to it.
Well, there may be the credibility, I guess, is the issue.
Well, if you send it to a real networking place, that will definitely be asked.
Yeah.
If you send to Infocom, that wasn't questioned but something else. So, okay, I think about how to extend this work.
But I think in
Yeah,
this,
sure.
this particular example, if you deal with more personal type of content,
Mhm.
for example, email file can follow you, right? So that type of caching is not generally considered when you look at popular distribution. You could get even more gain for that.
Right, so this is basically, okay, can you quickly point out, right, most of the gain is coming from prefetch or most of the gain is coming from caching?
So the normal.
Yeah, this is a very complicated graph. I don't think anybody understood it.
We actually have that graph from the paper.
No, no graph, just to summarize.
Yeah, so the normative parameter is around 0.8, and for that kind of this parameter, for our scheme, most of the gain comes from the
So
prefetch.
basically, if there's no locality, then prefetching helps the most.
Yeah.
If locality is very high, then caching is helpful.
Yeah.
Well, that's intuitive, right? But I don't expect to have such high locality in real world, right?
Well, according to some survey studies in the internet, the content retrieval is following ZIF, and ZIF parameter is 0.81. So
Yeah, actually in our results, we see that for ZIF around 0.8, the caching contributes more than the prefetching part.
if you consider internet data
Feixiong,
retrieval,
can you repeat the question?
Yeah, so their question is looking at the caching part and the prefetching part. Want to know which might be more effective when we have different ZIF parameter and request distribution.
But so point 8, it will also be impacted by the cache size. If point 8 is over a very long time, then if your cache is large enough, like CDN type of caching, yes, it may work. But if your cache is not that large, right? Even if over a long time, but within a short time frame, you probably don't see. Does that even make sense? Like, is
Small,
this?
for a small time frame, maybe prefetching is more.
I'm not sure
effective.
whether this same thing will be impacted by the time window, but that's something interesting to think about.
Yeah, I think these are all interesting questions that haven't been touched enough in this book yet.
Okay.
Feixiong, did you answer the question?
Yeah, we just had quite a few discussion on that. So yes, actually we had a figure about the separate contribution from prefetching and caching. Yeah, that result actually shows that when the ZIF is around 0.8, our prefetching actually contribute more than the caching.
Right. See, the thing is, when you have a very highly skewed request pattern, then LRU ends up being just as good as all the complications that you have, right?
Mm-hmm.
And it's only when you have a lot of spread in the request pattern,
Mm-hmm.
that's when you need the prefetching,
Yeah,
right?
yeah, agree with that.
But in your paper, you had separately evaluated the benefits of each of these components, right?
Yes, yeah. I have that result in the figure, no, in the paper, and the dissertation also. So we can refer to that in the dissertation. So maybe I can proceed.
Yeah, please.
So we can conclude that the EdgeBuffer improves the edge cache hit rate and could facilitate such mobile content delivery. And next, take a step back and look at the pros and cons of different caching scheme in ICN. So I look at this general ICN context, since ICN advocates in-network cache where each node might have a cache store. So this kind of network becomes a network of caches instead of a simple interconnection of nodes. For such cache network, it can be characterized by two dimensions: the content caching scheme and the request forwarding scheme. The content caching scheme including where to place the cache storage, whether to cache your content, and what content to replace. For the cache storage placement, we have pervasive caching and edge caching. For whether to cache your content, we have this leave copy everywhere scheme and leave copy down. Leave copy everywhere means when the data returns, all the in-route routers cache the data. While leave copy down means that only the first hop cache the data. For request forwarding strategy, we have the shortest path routing and the nearest replica routing. Shortest path routing means that the router simply forward the request to the original content store following the shortest path. While nearest replica routing, we assume that the caching location information is known by the node, and it could find out the nearest replica and forward it to that location. So the objective of this study is trying to understand different content caching and request forwarding choices particular, we want to understand whether pervasive caching and the nearest replica routing each brings significant benefits. And we want to see whether there is an ICN architecture that achieves most of the gain and is relatively easy to deploy. For this purpose, we look at these design elements, including the pervasive caching, edge norm. So for edge norm, it uses edge caching, but the total cache size in the network equals to the pervasive caching design. And we have leaf copy everywhere and leaf copy down scheme, and the shortest path routing and nearest replica routing. For nearest replica routing, we assume an oracle exists, so that the cache information is always known. We combine these designs to form several different representative designs. And we compare this design through an event-driven simulation. In the simulation, we have a content catalog of 100,000 files. And the client request for, we use a synthetic ZIF distribution. In the results, we look at these two metrics, the hit distance ratio and the network capacity ratio. Both of these two results are normalized metrics compared with a system without any cache. So we first look at a small-scale network scenario. Here we look at a 6-level binary tree, and all contents are placed at the root node, and clients connect to each edge node. In the evaluation, we vary the cache budget ratio. So this ratio is the ratio of the node's cache size compared to the total content size. And from the results, we can see that when using shortest path routing, the benefits of pervasive caching over edge caching actually is not that significant. As we can see from here, the benefits of using pervasive over edge is just 10%.
So wait, can you describe the y-axis on the graphs?
Yeah, so this here the y is the hit distance ratio. So the hit distance is the average distance from the client to the cache location where the content is found.
What's the
That's not a ratio.
What's the denominator?
Yeah, and the ratio is for that number compared with a system where we don't have any cache. Yeah, so this ratio
The base
is
case is no cache.
yeah.
So is that higher better or lower the better?
So for this one, the lower the better. And for this is the network capacity, so the higher it is better.
Right, so what's the denominator for the right, for the network capacity?
So for this denominator is also a system without any cache. And in addition, when we use nearest replica routing, we can see that sometimes the edge caching can even be better than pervasive caching. And also, nearest replica routing always achieves better performance than shortest path routing.
Yeah, can you provide some insight for that observation?
Yeah, so the insight why a pervasive caching its gain is not significant is also because of this kind of long tail distribution. For such long tail distribution, with a reasonable sized edge cache, we can already capture those popular content. While for pervasive caching, cache those less popular content in a far away locations might not bring much benefits. So that's why we can see the gain here is limited. And even sometimes the edge caching can be even better. And why nearest replica routing can be better than shortest path routing is, so yeah, actually here we assume that we know the cache information, so we can always forward it to a nearby location. So this can kind of balance the request load, and we can get richer.
Yeah, I mean, if you know the caching location, edge caching may be better, that makes sense, right? If you don't know it, you always go upward.
Yeah.
So.
Yeah, so that will be the shortest path routing. And later on, we will see how we can somehow approximate this nearest replica routing. So next, I look at a larger scale network scenario. So for this, I use a core tree topology. So I use the Aberdeen topology as the core nodes, and then I expand each core node with a 6-level binary tree. So here the contents are randomly distributed among the core nodes, and the client is connected to each edge node in the access tree. So we also look at the results. In the results, so the x-axis is the inter-intra-link delay ratio. So here I vary the ratio of the inter-domain link delay over the intra-domain link delay. And the y-axis, this one is still the hit distance ratio. So I compare with a system without any cache. And this is the total network capacity ratio. And from the results, we can see that the edge norm NRR achieves the best performance, especially with larger inter-intra-link delay ratio. In addition, we can see that the gain of using NRR over SPR is much larger than the gain of using pervasive caching over edge caching. As we can see from this set of results, the gain of when using nearest replica routing over shortest path routing is over 100%, while the gain of using pervasive over edge is just 8% improvement. So from this comparison study, we have these two observations. One is that the pervasive caching may not bring about substantial benefits than a simpler edge caching. The other is nearest replica routing could optimize content delivery, especially for a large network. Therefore, we want to advocate that a network should adopt edge caching and nearest replica routing. So we realize such a network using MobilityFirst. Here we adopt edge caching and we approximate nearest replica routing by using GNRS. Since GNRS manages the mapping between content name and all its locations, we can realize the anycast style content retrieval. But since approximating nearest replica routing requires us to have a network wide of cache information, we want to validate whether this is feasible. For this purpose, we use a hierarchical GIS. So we have a local name resolution and the global name resolution. For the global name resolution, it only manages the content name to the AS of that content. Because of this hierarchical GIS, a local content update doesn't cause global GIS traffic. In addition, since we use this edge caching, a content request can trigger at most one GIS update. This could also alleviate GIS update traffic. So we have conducted some background calculation on the global GIS update traffic. When assuming 25,000 ASs and 1,000 updates per AS every second, so the calculation result for the GIS traffic is around 10 gigabit per second. So this value is several orders smaller than the overall internet traffic. We have looked at the two problems in ICN, including how we can do the content transmission and transport control, and how we might do caching and prefetching. So next I want to look at how we can utilize this technique into a real use case. So I have worked on this satellite-based video delivery system. So I have this scenario here, shows the satellite CDN system. The SCDN provider is the content provider. It's connected to a central station. This central station has both terrestrial link and satellite link. And at the edge network, each edge network has an injection of the satellite, and also is equipped with an edge cache storage. So this system, we can use the satellite's capability of broadcast to distribute content to a wide area. So the edge network could cache this content and serve requests locally. This satellite CDN system is built as the field trial for MobilityFirst. And as I just mentioned, this system integrates the traditional terrestrial network with satellite network. So we can combine the benefits of two, including the terrestrial's advantage of handling individual user requests and the satellite's capability to broadcast the content to a wide geo-distributed area. We also utilize edge cache service to serve requests locally at the edge. So this figure shows the system prototype architecture. We built this system based upon the MobilityFirst architecture, MobilityFirst prototype. And we have add several core components to realize this satellite system, including a pluggable caching module and the satellite emulation and satellite transport. And we have emulated this system onto the orbit testbed using a bunch of emulation techniques, including we use VNet to separate the terrestrial domain from the satellite domain. So I want to have a summary of my dissertation work. So in my dissertation, I mostly look at two problems. One is how the data transmission is conducted in ICN and how we can design a transport protocol for that. The second problem is how we can do caching, since caching is a very important component in ICN. For this caching, I have proposed an EdgeBuffer framework and also conduct a general caching comparison. And after the investigation of these two problems, I look at how we can apply this research into a real-world problem. So I have worked on a satellite-based video delivery system. So these are my publications. I have published several papers for the first two projects, and for this project, we are still trying to submit it to a conference. And last, but most important, I want to thank Professor Yan Yong. She has guided me through all my PhD process and impact me on every aspect of my life. And also Professor Ray, he has also provided me with lots of guidance and support. And also Professor KK, he has given me lots of suggestions on my research and always motivates me to have a better work. And also I would like to thank all my committee members, colleagues, and friends and families. So without any of you, this dissertation is not possible. So last, I would like to see whether there is any other questions.